So today, oh, today we're going to start talking about electricity. So I'm going to first just kind of give you a little lecture, how to think about it. We'll talk about some simple calculations. And then after that, we'll take out some stuff and we'll start making some circuits, measuring the circuits with multimeters, and we'll just start getting used to the idea of working with electricity. This is going to be important for the end of the class as we start getting into robotics. Okay. So, and I would recommend taking notes on this if you have stuff you want to have. I mean, I guess there'll be PDFs of my notes, but you'll want to be able to write stuff down anyways as you go. So I'm going to first start talking about these ideas and the relationships between them. So the first one is electric potential. The second one is voltage. Current. And resistance. And we're just going to try to make sense out of the relationships between these things. How many people in here have taken or are taking Physics 2? Okay, not many, so a few. All right, well, electric devices are powered by current. So think of current as the thing that we want when we're doing any kind of electrical, manipulations. So current is the thing that powers devices. And current is defined as a movement of electrons. If you have a lot of current, you can power a big device. If you don't have much current, you can only power small devices. In order to understand how electrons move, so in order to understand current, it's helpful to think about an analogy with fluid flow. Let's think of it as water. Why not? Okay, so here's the setup that we're going to imagine. We're going to imagine potentially a long pipe. And we'll imagine a valve. Let's think of the valve somewhere in the middle. So that's something we can open and close to allow the fluid to flow. And let's think of all of this as full of, well, maybe to make more sense out of this, let's imagine valves on the two sides. So here's a valve, and here's a valve. So we can open those, and all this is water. Okay, so this pipe is all the way full of water. It can't flow anywhere because those valves are closed. Okay. But we can open those and let it go one way or the other. And then connected outside of the valves are two tanks. And we can control the pressure of these two tanks. Let's say they're connected to, think of them as connected to bike pumps. Okay, so there's a pressure over here. Let's call that pressure 1, and there's a pressure over here, pressure 2. Okay. And so what we're going to do is we're going to use the bike pumps to come up with pressures on these two sides. And then once we're at the pressures we want, we'll release the two valves and think about which way the water will flow. Okay. So if P1 is cranked up to, let's say, 100 psi, like the pressure inside like a bike tire, and P2 is, let's say, 20 psi, then when you release the valves, which way is the water in the pipe going to flow? Yeah. So release the valves, I guess open the valves. And the water is going to flow to the right. Okay. Then now refill it with water, close those valves. Make P1 equal to 120 psi. And make P2 equal to 10 psi. And open the valves. Water again is going to flow from the left to the right. Is there going to be any difference in the speed? Yeah, it's going to be faster, right? Because we have a bigger difference in those pressures. So water is going to flow to the right faster. Okay. Now if if instead P1 is equal to 40 psi and P2 is equal to 80 psi, and you open the valves, water is going to flow from the right to the left. Okay. Okay, there's one more thing that I want to say about this. So now let's say, the biggest pressure that I've talked about here is 120 psi. Let's say that we go to bigger pressures than that. Okay, so now we'll go to P1 is equal to, let's say, 140. That's about as much as you can probably pump up with a bike pump. But let's say that also P2 is equal to 140 psi. So this is a ton of pressure. Okay. And now you open the valves. Where is the water going to flow in this case? Yeah, it's not going to do anything because of the pressure. It's just going to do something because of gravity, So there's not any net, there's no net no net flow one way or the other. Okay, so what we have here is we can control the individual pressures on the two sides. We control the pressures on the individual sides. But the flow isn't determined by individual pressures. The flow speed and direction are controlled by the difference in those pressures. Okay. One other thing is going to factor into the speed of that water flow, and that is the thickness of the pipe. Okay. So the thickness of the pipe also affects the flow speed. If you have a really wide pipe, then you can get a very fast flow for a given difference in pressures. So a thick pipe allows a fast flow for a given pressure difference.
You're talking about the thickness of the actual wall of the pipe, right?
Not the wall, the gauge or whatever of the pipe, okay. Like how much. So think of them as being infinitely strong. We're not worried about the pipe breaking, but think about a straw versus like a plumbing pipe. For the same difference in pressure, the water is going to move more slowly through a straw than it is through a thick pipe. Okay.
You mean the radius?
The radius, yeah. Okay, so for a given like pipe radius, okay, the higher the difference in pressures, the faster the water is going to flow. Okay, but if you keep the pressures the same and change the radius of the pipe, water is going to flow faster through the bigger radius pipe. Okay, all these things are just sort of intuitive things that are, I think, everybody can sort of understand that. Anybody have any questions about this stuff? I mean, hopefully this is all kind of intuitive. This is how it would work. And we're going to use this. Yes?
Wouldn't it be diameter? So we're looking at the full.
Well, yeah, I mean, either one. Like if you, so, let me draw a picture. So if you have, so let's say that you have 100 psi over here and 20 psi over here. Okay, the water is going to flow through the pipe this direction. And if you compare this to this, with those pressures the same, make this 100 psi and make this 20 psi. The water's still going to flow that way, but more water is going, the water is going to flow faster. A bigger volume of water is going to pass any part of that tube. Than in this case. Okay? Does that make sense? I mean, if you wanted to have, like, get 10 gallons of water to go from one side to the other side, you would get that done faster with a wider pipe than a thinner pipe if you had with those same pressures. Okay. Okay, so now we're going to think about this stuff as analogies to these electrical things. Electric potential is like the pressure. Okay, so you can change the electric potential on the two ends of a wire, a conductor. And you can do that sort of independent of each other. What's really going to matter for creating electric flow is the difference in electric potential from one side to the other. Okay. The units of electric potential, the SI units, are volts. Okay, so electric potential uses units of volts, but it's not quite the same thing as voltage. Okay. If the electric potential is the same at two ends of a wire, then no matter how high that electric potential is, there's no flow of electricity. Okay, there's no movement of electrons. Voltage is now, we don't really have a word for pressure difference. It's just the difference between two pressures. But voltage is the difference between the pressures at the two ends. So the definition of voltage is the electric potential or let's say the higher electric potential minus the lower electric potential. Because this is just subtracting two electric potentials, this has the same units. So the SI units for voltage is volts, like you would imagine. The current is like, think of it as like the volume of water flow per unit of time, like the speed of the water flow. And it is always going to flow from the higher electric potential toward the lower electric potential. The SI units for current are amps. And we'll abbreviate that with a capital A. And then the last thing that I talked about that relates to the flow of water, the speed of water flow, was that pipe radius or that pipe diameter, okay? And the equivalent of that in electricity is the resistance. So that's the pipe thickness. So for a given voltage, would a lower resistance allow a faster, a bigger current, or a smaller current? If the resistance is lower, would the current be bigger or smaller for a given voltage? Bigger, that's right. So for a given voltage, a higher resistance reduces the current, and a lower resistance increases the current. Okay, so especially at first, I think it's a really helpful thing to always think about this analogy. You know, think of the voltage as the difference in pressures that's pushing this electrical flow through a conductor. Okay. And so what really matters is the flow of the electricity through the wire. But in order to get that wire to move, you need that voltage. You need that difference in electric potential. Okay. Okay, there was something I wanted to say here. Oh, one thing, like just right at the beginning while we're getting into this. So this is something to notice. So it's really electrons, the movement of electrons that causes electric current. So current comes from movement of electrons. And electrons have a negative charge, so which have a negative charge. But our conventions for most electrical calculations were already set by the time people discovered electrons. And it just happens, I mean, there was a 50% chance of getting it right, and it happens that people got it backwards. And so what we call a positive current is actually the opposite direction that electrons are moving because of their negative charge. Okay, so the direction of conventional current is opposite the direction of electron flow. Now, like everything that we're going to do in class, in this class, we're going to think in terms of conventional current. We're going to think of, basically, we're going to think as if there were positive charges moving around, and that's what electric current is. That's really the opposite of what's happening. Really, negative charges are moving in the opposite direction, but there's no reason for us to think about it that way. For any of you who end up doing electrical engineering, once you start getting into stuff where you have to consider quantum mechanics effects, then you will have to differentiate between the conventional current and what the electrons are really doing. But for now, we're just going to imagine positive charge moving around, and that's what electric current is. Okay? Any questions about that? That can be kind of a confusing thing. But in this class, we're not going to think about electrons. We're going to think about as if there's a motion of positive charges, and that's the direction of the current. Okay. So now that we have these four things, now we can talk about we can start to talk about some calculations. And the calculations we're going to do are going to involve Ohm's law. And Ohm's law says that the voltage is equal to the current times the resistance. Okay, so this is the voltage. This is the current. This is the resistance. And you can see that, like we talked about before, just intuitively, you expect for a given voltage, so for a given difference in electric potentials between the two ends of a wire, you expect if the resistance goes up, the current is going to go down. And that's what this relationship says. Like if you solve for the current, and let's say voltage is equal to 10 volts and resistance is 100 ohms, okay, then the current is going to be 10 over 100, so 0.1 amps, okay? If you want to increase that current for the same voltage, then you can reduce the resistance, make the energy flow more easily. Let's say the resistance then is 1 ohm, okay? And now you have 10 amps of current flowing through. Okay, so it makes sense. Intuitively, it makes sense. But this is the mathematical relationship. Okay, so let's start by thinking of let's think about a case where we have a 9-volt battery. Let's say this is the positive terminal, this is the negative terminal, and this is 9 volts. And what that 9-volt battery means is that the positive side electric potential is 9 volts higher than the lower side, okay? It could be an electric potential of 1,000,009 volts, and then an electric potential of 1,000,000 volts. All that matters is the difference between them for pushing current through a circuit, okay? And we'll connect a wire to the positive terminal, and then we'll connect one end of that wire to a resistor. And this isn't a schematic diagram. This is just sort of drawing a picture of what this would look like. These resistors have colored bands on them, and I'll talk about what those mean. But let's say that, so we have this 9-volt battery, and let's say that this resistor is 1,000 ohms. I didn't give the SI units for resistance, but sorry about that. The SI units for resistance are ohms, and it's denoted with a capital omega, like that horseshoe. Okay, so if this is your circuit, let's figure out what the current is through this circuit. Well, Ohm's law says that 9 volts is equal to the current times the resistance, and the resistance is 1,000 ohms. So now you can calculate the current is equal to 9 1,000ths, or 0.009 amps. And since for most of the things we're going to be doing, an amp is a lot of current. Usually we'll be dealing with much smaller currents than an amp. A lot of times you'll represent currents in milliamps. And so I'll write this as 9 milliamps. The next thing we have to know is what's the direction of this current. Okay, and so what this means, the positive side over here on the left, current is always going to flow through your wires from the positive electric potential toward the negative electric potential. Okay, that's the positive is the higher electric potential and the negative is the lower. So the current here is going to flow this way. That's going to be important because we're going to eventually be dealing with a lot of devices that only work when current flows one way through them. Okay, so yeah.
This is the conventional flow, right?
Yeah, everything I'm talking about is conventional, that's right. Any other questions right now?
You're not going to want us to do like any of the other metric sizes for stuff like distance. Like,
Nope, we're going to do everything in SI units.
No, I mean like because you did milliamps. That's why.
Pretty much milliamps is what we're going to be working with for our electronics. So that's about it, I think.
Okay.
Yeah. Any other questions? Okay. So now the one more thing I have to talk about for calculations is resistors in series and parallel. Okay, so first I'll talk about series. So that is, so any two devices that are in series the meaning of that is that electricity goes first through one device and then through the other device. So if I draw a circuit where you have two resistors in series, so there's the positive side, there's the negative terminal. A wire goes from the positive to one resistor. And then another wire goes to the second resistor. And then back to the negative terminal. um, for devices in series, the current is the same through each device. But the voltage is divided. You know, let's say the voltage is divided between them. So if we want to find the voltage and the current in each resistor in series, the first step is we'll imagine that those two resistors in series are a single resistor. So we're going to lump the two series resistors into a single resistor. And the combined resistance of the two is just going to be the sum of the individual ones. Where like, so this would be R1 and this would be R2. And now we're saying, okay, we're just gonna imagine that this whole thing is packaged as a single resistor. And the resistance of that whole thing would just be the sum of those two in this case. Second, we're going to calculate the current using Ohm's law. So we're going to use voltage equals IR to calculate the current. And then once we have the current, I said that for these resistors in series, the current through both of them is the same. So now we know the current through each one of those resistors. So now we know the current through each resistor. Use Ohm's law again to calculate the voltage across each individual resistor. Hold on a sec. Okay. So let me do, I'll do one calculation, show you how this works, and then I'll give you time to work through one. So for the first example, and now I'm going to introduce this. I've been just drawing these pictures of wires and batteries and stuff. But I'm going to introduce some schematic symbols that mean the same thing. So if you see something like this with a long side and a short side, that's a battery. And the long side is the positive, the higher electric potential. The short side is the negative. So it won't usually show the positive and negative, but that's what those long and short sides mean. Three jagged things like this, that's a resistor. A circle with a line coming from it is a voltage source. And it'll always be given with the electric potential that's provided here. So this would say like plus 5 volts, for example. And then the other symbol you'll see is something like that. This is the symbol for ground. And that you'll treat as 0 electric potential. So there are two ways that you're going to see voltage represented. You'll see it represented as a battery where it tells you the voltage between the two terminals, or you'll see it as a voltage source and a ground that also tells you the difference in electric potential between the one side and the other side. Okay, so here's the first example. So let's say we have a voltage source of 5 volts. And 2 resistors and a ground. And let's say that the 2 resistors, we have one that's 220 ohms and a second one that's 90 ohms. And we want to calculate the voltage across each resistor. and the current through each resistor. So I'm just going to go through the steps that I outlined here. You have to recognize that these are in series. And they're in series because this is a case where the electricity, the current, has to flow through one. And then once it's gotten through the one, then it goes through the other one. And they don't have any other options of, the electricity flow doesn't have any other option of where to go. Okay? And in this case, the current has to be the same through both of these. Okay, so the first thing we're going to do is we're going to treat these series resistors like they're a single resistor by just adding those resistances. So I'll treat this as this circuit to start with, where we have plus 5 volts here. What's the resistance of that combined resistor? 310. 310, yep. So 310 ohms. And now we can use Ohm's law. And it says that, so the potential difference between the two ends of this circuit are 5 volts. So we have 5 is equal to 310 times I. And so then do the algebra and you get that the current is equal to 0.016 amps. Or if you want to do it in milliamps, that's 16 milliamps. Okay, but so we know that the current is flowing this direction. And we know that that's the current in each one of those resistors. Now we want to figure out the voltage across each of those two resistors. So now we'll like re-expand it. We have the 220 there, the 90 there. We know that the current here, that I'll symbolize with the line showing the direction, is 0.016 amps. And we know that it's the same current over here on this one, 0.016 amps. And now for each of those individually, we can use Ohm's law. So the voltage across that first one, I'll call it the voltage across the 220, is equal to 220 times 0.016. And that's 3.55 volts. And then for the 90, we have the resistance of 90 ohms times the current of 0.016 amps is 1.45 volts. So if I write this whole thing out again, this one has a current of 0.016 amps and a voltage of 3.55 volts there. The positive and negative here, that polarity shows which direction has the higher electric potential and which has the lower. And then for the second one, we have a current of 0.016 amps and a voltage of 1.45 volts. Any questions about that? Yeah.
Will we still keep the 5 at the very beginning or no?
Oh, yeah. I was just writing what we didn't know so far, but any other questions about that? So let me give you one problem to do, and then we can talk about parallel stuff. So let's say this time, let's say that we have the voltage is provided by a battery, and let's say that the battery is 12 volts, and the positive is to the right, and we have a resistor there, and a resistor there, and let's say this is 10,000 ohms, and this is 1,000 ohms. And we want to calculate the current through and the voltage across each resistor. Okay, so take a few minutes, see if you can work through that. Feel free to talk to each other, compare answers. Feel free to ask me stuff if you get confused about something. And then after I give you some time to work through it, I'm going to go through it, and you can just sort of check your steps and make sure you're thinking about it right. Okay, I'll pause this for a sec. All right, so I'm going to go just through those 3 steps again. So the first thing I'm going to do is, always the first thing you need to do is verify that these are in series. We haven't talked about parallel resistors yet, so clearly they're in series, but you can see that as current flows from the positive terminal of the battery toward the negative, it has to go through this one, and then it has to go through that one. So that's the definition of series. And so I'm going to first simplify this circuit into a battery and a combined resistor. And the combined resistor, when they're in series like this, is just the sum of the two. So this is 11,000 ohms. And this is 12 volts, where the positive is this way and the negative is this way. And now we can use Ohm's law to figure out the current through both of those 2 resistors. So we have 12 is equal to 11,000 times the current. And so 12 divided by 11,000 is 0.00109 or 1.09 milliamps. Okay? And now that we have the current through each of these, now we can go back to the full circuit. So there's the 10,000, here's the 1,000. We know that this one has a current going this way of 0.00109 amps. This one has a current going this way of 0.00109 amps. And so now we can use Ohm's law on both of these. So for the 10,000, the voltage across the 10,000 ohm resistor is 10,000 times 0.00109. And so you get 10.909 volts. And the voltage across the 1,000 ohm resistor is the resistance of 1,000 times the current. Which is 1.091, if you round it, volts. And so we have a voltage across the 10,000 ohm resistor of 10.909 volts. And a voltage across the 1,000 ohm resistor of 1.091 volts. And again, I mean, they always have to add up to the total voltage coming from that power source. So if you add those up, they give you 12 volts. Okay. So this is a case where we have a very big resistor and a much smaller resistor, you know, that's a factor of 10 to 1 for the resistances of these two. And you can see that the effect of that is the big chunk of the voltage is going to be across the resistor with the highest of the higher resistance. Okay. All right, let me tell you something about this to keep in mind. So notice resistors in series divide voltage. And so that's something we can take advantage of. If we have a voltage source that's higher than the voltage we want to go to a particular device, then we can use series resistors to reduce the amount of voltage that's felt by a certain device if we're trying to power a motor or something like that. Okay? So we can use that to reduce the voltage for a device. Any questions about that? Okay, so now that's if your resistors are in series. Now, what happens if your resistors are in parallel? Let's see, how did I write this? Okay, so when two things are in parallel, electric current has the choice it can choose whether to go through one device or the other. So like, for example, if you have your battery and the wire goes from the positive terminal to, let's say, here's a resistor, and I'll call this one R1. Plus you. And then there's also another resistor here, R2. And notice that this branching of the wires means once the current that's flowing from the positive gets to this junction here, it can, it can't really decide, but you can think of it as like, if it was a person, it would have to decide whether to go through R1 or R2. Okay, so that's different than the series. In the series, it would have to go through one of them, and then it would have to go through the other one. This one, it either goes through one or the other one. Okay. So this can be shown on schematics a few different ways. You really just have to think about it as whether the electricity is going to go through either one or the other, or whether it's going to go through both of them. So a schematic here would look like this. Okay. For parallel devices, the voltage across the devices is the same.
No book. No, other way.
And the current is different. So that's the opposite of the way it worked with series. Okay, so remember that series can divides up the voltage. Resistors that are in parallel like this divide up the current that flows. So the steps we're going to use for these are, first, the voltage across each resistor is the total voltage. And then we're just going to use Ohm's law for each resistor. To calculate each current. Okay, so let me do an example. So let's say we have plus 6 volts here. And let's say we have 100 ohms for that resistor and 1,000 ohms for this resistor. And we want to calculate the voltage and the current for each resistor. Well, your first job is to recognize that these resistors are in parallel. So notice that once you get to this junction here, electricity can either go across the 100 or it can go across the 1000, but it can never do both. Okay. Well, the first thing that we recognize then, once we realize that these are in parallel, is that the voltage across each of these resistors is the same as the total voltage of the system. So I'm going to draw it again. We know that electricity is flowing from the higher electric potential to the lower electric potential. So it's flowing this direction. And so the voltage in this resistor is 6 volts with the polarity shown there. And following from the junction, following that same direction, the polarity for the 6 volts on this one is this way. Okay. And now we're going to use Ohm's law. So for the 100 ohm resistor, the voltage across the 100, which is 6, is equal to the resistance, 100, times the current across the 100 ohm resistor. And so the current is 6 divided by 100, so 0.06 amps. And then for the 1000 ohm resistor, the voltage is 6. 6 is equal to the resistance, 1000, times the current through that one. Do the algebra, and you get that I1000 is equal to 6 over 1000, so 0.006 amps. Okay, and so now we know that the current is going to go this way through this resistor, and the current there is 0.06 amps, and it's going to go this way through this resistor, and that current is 0.006 amps. Okay, well, preferentially, electricity is going to take the path of least resistance, and you see that here. So this one had a much smaller resistance. This one had a much bigger resistance. And so what we see is that most of the current goes through the less resistance. Only a little bit goes through the really high resistance. Okay. And that's why, by the way, a short circuit is when, so in a short circuit, something would happen so that electricity can travel freely with no resistance instead of going through this resistor. Okay, it's like a shortcut instead of going through the resistor, going through the hard part. So if this had zero resistance, all the electricity would just flow with no difficulty at all through here. None would go through here. You'd end up damaging something in your, you know, if you have like sensitive circuits, some kind of microprocessor or something, you'd get a very high current because you have very low basically zero resistance, and the effect would be to break something in your circuit. Okay, let me give you one of these to do. So let's say we have a 9-volt battery. And let's say that this one is 250 ohms, and this one is 300 ohms. And you want to calculate the voltage and current for each of these resistors. Okay, so we know that the voltages are the same for both of these. We know that current is going to go from the positive terminal of the battery towards the negative. This electricity is going to get to this junction and go this way and this way. And so I guess I'll draw this again. We know that this is going to be 9 volts this way. And this one is going to be 9 volts with this polarity just by the direction of the voltage drops. Anyone have any questions about how I understood that? And now we can go and calculate the current. Well, we know the currents are going to go this way and this way. We just have to figure out the magnitudes of the currents. So first we have that 9 volts is equal to 250 times the current of the two across the two through the 250 ohm resistor. And we get that the current through the 250 is 0.036 amps, 36 milliamps. And then the 300, so we have 9 volts is equal to 300 times the current through the 300. And so the current through the 300 is 0.03 amps. So I can write it on here as this one is 0.03 amps, this one is 0.036 amps. Okay. All right. Well, we are not going to get to the multimeters today, but let's start getting used to some of the electronic components. Okay, so the first thing that I want to talk about is how to know what resistors you're working with. So the resistors on the bands work. A black band means 0. A brown band means 1. Red is 2. Orange is 3. What? Oh, yes, right. I forgot that was there. Thank you. Well, I'm going to put it in your notes here anyways, but I guess I don't have to go so slow. Yellow is 4. So hopefully what I say will match up with what it says over there. Green is 5. Blue is 6. Violet is 7. Gray is 8. White is 9. Okay, well, the code's over there. I don't know what's going on with my computer, but and then if you have a gold band, that means plus or minus 5% precision, and a silver band means plus or minus 10%. Okay, so take out the one that said, oh, and the way you read this is go to the side that's not blue, that's not gold or silver. And those first 3 bands, you'll read them like this. It's always going to be the first color is the first digit. The second color is the second digit. And then you're multiplying that times 10 to the third digit. And then the fourth is the precision. Question?
Can you repeat that?
Yeah. So the first color on the band is going to be this. That's the first digit of a number. The second color on the band is going to be the second digit of a number. And then you're multiplying that 2-digit number by 10 to the third color. And then the fourth one just tells you the precision of that resistor. So let's get out, everyone get out the one of the ones that, so you have a set of resistors that says orange, orange, brown, and then gold is the precision. So yeah, the first two colors are orange and then brown. And if you hold it backwards, then the first color is gold. And that's how you know, like, okay, gold and silver means something else. Oh, okay, right. Are you guys finding it? Orange, brown. Yeah, right, exactly. Anybody having trouble finding this thing? Okay, so what's going to be the resistance of this resistor? Well, using this code, the orange means 3, okay? So if this thing is orange, brown, that means 3 times 10 to the brown is 1. So 33 times 10 tells you that this is 330 ohms. Okay?
Oh, so that's not multiplying 3 times 3. It's
Right. That's right. It's the 2 digits. Correct. Yep. And let's see. The other ones we have are, I think, the other ones we have are a 1,000 and a 10,000. So like, the 10,000 is brown, black, orange. So that means the brown is 1, the black is 0, and then you're multiplying that times 10 to the third. So you have 10 times 1,000 is 10,000. The other one we have, I might as well write that one down. So brown, black, red. The brown is 1, the black is 0, times 10 to the red is 2. So that's 10 times 100 is 1,000 ohms. So those are the 3 resistors you have in there. Later on, if you need other resistors, we have boxes and boxes of them in the cabinets of different values. Okay, so for now, put those resistors back in the right spots with the other ones. And we're going to talk about something else. The next thing that we're going to use is the breadboard, this thing. I don't know why they call it a breadboard. Maybe that's what breadboards used to look like. And the breadboard is just designed to make it really easy to connect wires together. And so the way it works is like this. I'll draw the top of it. I'm going to draw these as connected lines. I'm not going to draw all of these, but the way it works is you have holes to push wires into. And the red lines that I've drawn, all of those are connected to each other electrically. So if you connect one wire to this point and one wire to this point, it's like connecting those two wires to each other. Okay? And the same thing with the horizontal ones. If you connect a wire to this point and a wire to this point, it's like you've connected those two together. Okay? And so we're going to use this breadboard to make our first little circuit, and we're just going to show that it works by connecting it to an LED. So what we want to do is, so the first circuit with the breadboard, we want to go from the 9-volt battery to a 1,000 ohm resistor to an LED that the symbol looks like this. And that 9-volt battery is going to turn on that light if we do this right, okay? So what this is going to look like physically is we have the 9-volt battery with the positive and negative. We're going to connect it to the 1,000 ohm resistor. Then we're going to connect that to the LED. And the LED is, I mean, you know what the LEDs are. But the one thing you need to know about this is all the LEDs have a long side terminal and a short side terminal. The long side is the positive. So that's, if you hook it up the wrong direction, it won't light up. Okay, so you want the long side to be the one that's on the side of the positive terminal of the battery, and the short side to go toward the ground. Okay, so you can use these things to connect to the battery terminals, and you can use the wires and the breadboard to hook up the other devices. So see if you can figure out how to do this using the breadboard. Feel free to come up here and I'll hook it up and you can see how I'm doing it. Oh yeah, so use, I'm gonna put like a wire into the breadboard, and then I'll just use the alligator clip to clip to the free end of the wire. You know what I mean? If you accidentally use a 10,000 ohm resistor, it'll still work, but it'll just be really dim. So remember the 1,000 ohm resistor, the third, it's brown, black, and then red instead of brown, black, and then orange.
Oh, he's home. Yeah. Oh, we're not gonna weekend. If you want.
And I didn't check all these. I didn't check all these LEDs. I know the small red ones work with this amount of current and stuff. So that's what I'm going to use.
Oh. Right. So how can we plug it in here?
Yeah, you can plug it right in there. So like I'm going to go. I'm going to do it like this. So I'm going to have the. So I'm going to have the battery go to this, and then it connects through the resistor to the positive side of the LED, and then the negative side of the LED goes to a different line. Then I'll have a wire coming out of here. And then I just, I'm gonna.
It have to be the same row, right?
The same row, yep. Or if you're using the long ones, it can be all the way down that thing.
Three times. You got a minute stop. Oh, that's it. So it's kind of still. Oh, it's just her.
How's that going? You got it to go yet?
If we connect it like this, are they gonna have different resistance? Like
Yeah, and so that won't work because so since they're all connected, it's like these devices on each other. You're just having electricity flow freely through the battery.
so these bursts from the red lines, others
Those do not break.
those don't break.
Right. So instead, you want to go. So you can go like here, here.
Yeah. So the green is breaking now. Does that mean
Here,
higher?
here, say, and then here.
Or we could do see how bright.
I need to know what kind of voltage these lights are.
So, like anytime you're,
We don't have.
so anytime you're on those, so like if you put a wire here and then another wire here, it's like soldering these two wires together, you know. So if you put a resistor there, it's really just like soldering the two ends of the resistor together, and no electricity goes through it, you know.
So I want to understand like what ends up here. So
Yeah.
Do the red dashes mean like all of these pins?
Nope. The vertical ones and the horizontal ones are independent. They do not with each other. So we had to put this resistor over here so that these.
So, but are all like these pins like this way?
Those five are
Those five, and then
yeah,
these five are connected, and these five are connected. Okay, and then but these are connected all.
all the way down.
Okay. Makes sense. What's up to exam?
Anybody? Oh, that's correct. Yeah. Yeah. Oh, okay. So yeah. So you can do so
They have this for the. It's like a wheel, but have. The teeth on that, make a gear. Yeah, the gear. So it's making movement.
so now I'm gonna connect, this here is connected to this, right? So now we're gonna connect another one.
Wait, so there's basically just a connecting wire.
So it's not, it's two weak.
Yeah, that's what those lines are like on their bases you need.
And now you
It's like a bus bar that they're all attached to. So all of these, I imagine, spans the whole light. So if you want to connect those, you can power off here.
But the reason is small and I try worrying that
That's what we're gonna do in series, we just put it, we can do a lot of, I think. No, to do series, we have to do it, there we go. I don't think it'll lock.
I'm sure I don't.
I mean. Kind of jump from one leg down.
What is this? Like around size and then just like this finger around that, just the opposite direction.
Yeah, that's how it's, with a red, you can see a little better. I think this takes a little more current.
No, they're in series now. This 100 has to go back down the leg.
This goes. Oh, class is done. So if you have any questions, I'm happy to come around and look at it. But look for a homework assignment today. It'll be some perfect stuff.
Wait, Yep.
Oh, can you put the batteries back up on my desk? And then, yeah, right. Good question. All the other stuff, put it back where it belongs in the box, and then stack the boxes back over here. Okay. So, like these 5 tools are all connected, and so if you terminate this device on the same road, it's like having them connected. And so no electricity will go through that. So instead, with the device, you want to have one and one place and one go up there. And this one. We'll connect this to the positive.
Yeah, I put it back.
Thanks, people. Thanks. Thanks, people.
A little bit. You have them.
We are not really going to use that stuff for our circuit. We won't really need that. Mostly, we just need to be able to control like voltage and current that's coming from the new program, you know? So that's pretty much all we're not using alternating currents or anything, just direct current, yeah.
There's like a project with this, what is that project gonna be?
Yeah, it's gonna be, like designing a robot that does some kind of thing. And so it'll, with a, so you're gonna program a microcontroller to do, I mean, I can show you some videos of like what people have done in the past, but,
What kind of stuff do they do on this? The robot.
I've seen people make great mixers, I've seen one sort of play ping pong. I've seen a lot of cars that follow like lines on the floor. Those just pop into my head. But it's going to be a cool project. You're going to really like it. I mean,
When do we start that?
like weeks are left. We do it for the last 6 weeks of the semester. So yeah, probably right after spring break, pretty much. Yeah.
Cool.
Yeah, it is going to be good. Everybody seems to like it.
Nice.
All right, see you later. See ya. Hi.
I had a couple late work.
Okay, yeah.
One of them I sent email.
Yeah.
And the other one, I'll send it later, maybe tomorrow morning on email. Is that
Great.
all right?
Yes, that's perfect. So,
Okay.
people ask me sometimes like, oh, I emailed you something and it's not graded yet.
Yeah.
I just haven't gotten to the email stuff yet, but I
Okay.
will grade everything that comes in from email.
Okay.
So if you can just make it clear in the subject what assignment it is, it
Yep.
just makes it easier for my bookkeeping.
Okay.
All right.
Thank you.
Yep. See you later.